Okay, hello everyone. In a new video. In this one we are going to solve an exercise related to mechanics and the chapters of mechanical actions, equilibrium of a body and Archimedes upthrust. This exercise was a previous one in the brevet exams in 2016 first session, third exercise. The title of this exercise is Determination of the Density of a Liquid. Consider a solid cube S of side A is equal to 3 centimeters. So knowing that centimeter is not the SI unit of length, in order to convert from centimeter to meter, we simply divide by 100. Then 3 divided by 100, then the side of this cube is given by 0.03 meters. Knowing that this solid is a cube which is classified as a regular shape, so its volume can be directly calculated from this side. We suspend S at the lower extremity A of spring R. The other extremity of the spring is fixed to a support adjacent figure. So they mentioned this figure, now we can use it. So this is the solid S, this is the spring R connected to a support, and the other free end of the spring, which is denoted by A, is connected to the solid S. The stiffness of the spring is given by K is equal to 10 newtons per meter. Here, the stiffness of the spring is given by 10 newtons per meter, which means that in order to elongate the spring by 1 meter, we need to apply a force worth of 10 newtons. Take G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of Earth, which means that each kilogram is being acted by the force of gravity worth of 10 newtons. At equilibrium, this is important, so at any moment in this exercise we can use the condition of equilibrium. R is elongated by delta L, given by 7.3 centimeters. So knowing that centimeters is not the SI unit of length, in order to convert from centimeters to meter, we simply divide by 100. Then 7.3 divided by 100, then the elongation delta L is given by 0.073 meters. Now number 1, determine using Hooke's law the magnitude T of the tension T vector of the spring. So they are telling me which law we need to refer to. So always in physics we need to mention the law that we are using. So let's say apply Hooke's law. Hooke's law is given by the tension is equal to the stiffness, which is denoted by K, multiplied by the elongation, which is denoted by delta L. No need to construct a formula for this triangle because this is the quantity that we want to calculate. K is given by 10 in the SI, and the stiffness is given by 0.073. Now plugging this on the calculator, then the tension T is given by 0.73. Since both K and delta L are expressed in the SI, so the value of T will be expressed in the SI, which is given by newtons, and the value of T is given by 0.73 newtons. Now number 2, S is at equilibrium under the action of two forces, its weight W and the tension T vector. Part A, give the condition of equilibrium of S. So here it is at equilibrium. How do we apply this condition? Always as a title we write at equilibrium. On the left hand side of this equation we write the sum of forces acting on the solid S, and they are given by the weight and the tension. So weight vector plus tension vector, and on the other hand side of this equation we write the zero vector corresponding for the equilibrium, and we don't forget vectors on all of these three quantities and especially the zero. Now moving T to the right hand side, we have that W vector is equal to minus T vector. What does the first equation tells us? That the effect of both forces acting on the solid S cancel each other, whereas the second equation tells us that both forces have the same line of action, opposite direction and same magnitude. And now in part B, deduce the magnitude W of the weight W of S, and by deduce it means that we need to use the previous part. In the previous part we have determined the condition of equilibrium, and we already know the magnitude of the tension T. So from this equation we can say that we are interested in the magnitude So the magnitude of this equation is given by, now we drop down the vectors and remove the minus sign, so we have that W is equal to T, but we know that the value of T is given by 0.73 newtons, then the value of W is given by 0.73 newtons as well. So here the value of W is given by 0.73 newtons. Now in number 3, show that the volume of S is given by V is equal to 2.7 times 10 to the power minus 5 meter cube. So recall that S is classified as a regular shape and its volume can be calculated using V is equal to A to the power 3. The side is given by 0.03 meters. So 0.03 raised to the power 3. Plugging this on the calculator, then the volume is given by 2.7 times 10 to the power minus 5. Since the side is expressed in the SI, so the volume V will be expressed in the SI, which is meter cube. Then the volume V is given by 2.7 times 10 to the power minus 5 meter cube. Now part 4, S is now totally immersed in a liquid L, so this is important, it's totally immersed. And by this it means that we have that the immersed volume is equal to the total volume of the solid S, which is given by 2.7 times 10 to the power minus 5. Of density rho L, so the density of the liquid is denoted by rho L. The magnitude of the tension of the string becomes T prime is equal to 0.41 in newtons. So this variation of the magnitude is due to Archimedes' upthrust F exerted by the liquid on S, and this is very important. And here by the variation they mean the difference. So the difference in what? The difference of the magnitude. So here magnitude refers to which force? To the tension or to the weight. So because in the previous statement they mentioned the tension, so they are talking about the tension. So previously the tension was given by 0.73 newtons. And now T prime is given by 0.41 newtons. So they are telling us that the difference in the tension from 0.73 newtons to 0.41 newtons is due to the presence of the Archimedes upthrust force exerted by the liquid on us. Part A, give the line of action and the direction of F. So we know that always the Archimedes upthrust opposes the action of the weight, knowing that weight acts vertically downward, so F acts vertically upward. Then the line of action is given by vertical, and the direction is given by upward. Now part B, they are telling me show that the magnitude of F is equal to 0.32 newtons. Now the value of F can be calculated using the difference in the indication of the spring balance or the variation of the magnitude. So F upthrust, which is denoted by F, is given by the real weight minus the apparent weight. Here notice that the real weight is denoted by W. So let me write W. Why this weight represents the real weight? Because notice that in the first part of this experiment, when we have determined the magnitude of W, we didn't have any weight. So we know the value of W. It's left to determine the value of W apparent. But we know that T prime is equal to W apparent. Why? Notice that here in this part B, we have verified that T is equal to W. Now when T becomes T prime, then rho will becomes W apparent, because T prime correspond for the tension when the solid S was completely immersed on the liquid, and in this case W doesn't correspond anymore to the real weight. However, it will correspond to the apparent weight, and in particular here, because they are telling me the magnitude of the spring becomes T prime is equal to 0.41 newtons. This variation of the magnitude is due to Archimedes upthrust F exerted by the liquid on S. So in this case we have T prime is equal to W apparent. So knowing that the value of the real weight is given by 0.73 minus the value of the W apparent, which is 0.41. Why W apparent is given by 0.41? Because W apparent is equal to T prime and T prime is equal to 0.41 newtons. Now, okay. So plugging this on the calculator, then the value of F is given by 0.32. Since both W and W apparent are expressed in the SI, so the value of F will be expressed in the SI, which is in newtons. So F is equal to 0.32 newtons. Now in part C, determine rho L. Let me make some space here. So we need to determine rho L, knowing that previously we have determined the value of F. The value of F and rho L are related via the following formula, that F upthrust is equal to the density of the liquid times the volume of the immersed part times G. We are interested in determining the value of rho L. So constructing the triangle of this formula. So okay, before we construct the triangle, and here let me say that okay, F is given by 0.32 newtons. So in order to determine the value of rho L, we need to know the value of F upthrust. So we know the value of F upthrust, and we need to know the value of G. Okay, we have that G is equal to 10 newtons per kilogram. It's left to know the value of the immersed volume. Here, because they are telling me that S is totally immersed in the liquid, so let's justify why Vi is equal to V. So since S is completely immersed in the liquid, then Vi is equal to V. Okay, so usually they give half a mark for this statement. So now constructing the triangle of this formula, here because we have multiply, then F upthrust will be at the top, rho L, Vi and G at the bottom, knowing that we are interested in determining the value of rho L. So putting our hand over rho L, which is denoted by rho L, is given by the value of F upthrust, which is denoted by F. And here we replace Vi by V multiplied by G. The value of F is given by 0.32. The value of V is given by 2.7 times 10 to the power minus 5. And the value of G is given by 10. Plugging this complicated fraction on the calculator, then the value of rho L is given by 1185.19. So here we have a comma. Since everything is expressed in the SI, the value of F, V and G, then the value of rho L will be expressed in the SI, which is kilograms per meter cube. Then the value of rho L is given by 1185.19 kilogram per meter cube. And by this we have finished solving this exercise. Hope it was beneficial for you guys out there watching it, and see you soon on another one.